mic, I'll make my joke that those of you that know me and my voice, you would know that I don't need a mic. So I'm going to try to talk very quietly into it. But welcome everybody. My name is Cheryl Mills Englander. I'm the chair of the Sustainable Change Alliance Foundation, and I want to welcome you to our hydrogen panel. It's a panel we've wanted to do for a very long time. COVID, like many activities, raised its ugly head, so we had to be a little bit patient. So we're absolutely thrilled to be able to bring this to you today. And of course, I have a little bit of a text on Sustainable Change Alliance. So, we are an impact-oriented, member-based, not-for-profit educational group. We are focused on impact investing, which we define as bringing financial and other resources to double and triple bottom-line organizations that are trying to address big social, environmental, or health-related issues, and trying to do that in a sustainable manner. Some of those organizations are for-profit, some are non-profit, and some come from the independent sector. And you will not find investors with bigger hearts than those that are members of SCA. I would like to acknowledge our hardworking and dedicated SBA board members in the meeting. If you're a board member, can you raise your hand so everyone knows who you are? All right. Thank you for your work. And I want to say thank you to all of our members of Sustainable Change Alliance. Without you, we can't make these happen. And finally, we need to recognize our sponsors who are also critical in bringing programming like this to you. Our founding sponsors are Argyle Capital Partners, Impact Family Office, Maps.com, Solgenics, and the Taps Group. Our platinum sponsors are Nixon Peabody Law Firm and Cottage Hospital, and our silver sponsors are the Santa Barbara Foundation and the American Riviera Bank. If you're not a member yet of the Sustainable Change Alliance, I would love to encourage you to check us out and consider joining. One thing I absolutely adore about this group is a diverse array of issues that we bring up, and we have fun while we're doing it. So we go, for example, from hydrogen power to the housing issues of Santa Barbara to the blue economy and preserving our oceans. So you get a huge array of topics when you're a member of SCA. So without further ado, I'd like to introduce Ivor John, who is going to take it away, and I'm supposed to rip the mic out and give it to him.
Thank you, Sarah. I'm going to stand for a minute and then I'll sit down once we begin the discussion. But good afternoon. Thank you all for coming, and thanks to SCA for putting this on and inviting us to participate. It's a fabulous turnout, so I'm thrilled to see you all and hope you are inspired and have greater awareness of what the hydrogen economy is looking like after we finish this little discussion. So I am Ivor John, and I'll be facilitating, and the topic is going to be how early stage investments can leverage the emerging hydrogen economy. So I'm a managing partner with Hydrogen Power Partners. Here in town, we're a new hydrogen venture capital fund, and we've just launched, and we're focusing exclusively on hydrogen and hydrogen in the early stage innovation side of startup companies. In the room today with me are Stephen McIntosh, who you all will know, I'm sure, my partner, and Steve Warsman, who is my other partner, and that's our team. So we're really fortunate now to have two very distinguished guests to engage in this conversation with me. So I have got bios for these two, and they are super impressive. I've abbreviated them, but they're still very, very, a little bit long, but it's worth sharing. Professor Jack Brouwer. He's a professor of mechanical and aerospace engineering and director of the National Fuel Cell Research Center and director of the Advanced Power and Energy Program at the University of Irvine. Jack's leadership has led NFCRC and the APEP to focus on research and testing on high-efficiency environmentally preferred energy systems, conversion, power generation, technology advancements, and fuel cells and gas turbines as the principal targets. Current research projects: ultra-high efficiency and low ultra emissions, high-temperature fuel cell systems, renewable power intermittency and integration, advanced fuel cell and gas turbine dynamics. I can go on, you get the idea here. So, prior to joining UCI, Jack was at on the faculty of the University of Utah and staff scientist at Sandia National Lab, Jack Brower. And also with me, we have Dr. Anita Sengupta. Anita is an aerospace engineer and a rocket scientist who over more than 20 years has developed technologies that have enabled the exploration of Mars, asteroids, and deep space. She worked for NASA, where her engineering projects included development of ionic propulsion system for the Dawn mission to the main asteroid belt, and the supersonic parachute that landed the Curiosity rover. I'm emotional, it's amazing, on Mars in 2012. After she left NASA, Anita became Senior Vice President of Systems Engineering at Virgin Hyperloop, an all-electric transportation system, and she next spent several years in the battery-powered eVTOL, vertical takeoff and landing airline sector. So in 2020, she founded Hydroplane Limited to develop a novel hydrogen fuel cell powered electric power plant for aircraft to enable truly sustainable aviation. Anita is a research professor at USC, and she's an instrument-rated pilot and a captain in the US Air Force Auxiliary. So welcome to them both. So to begin, a few words, I'm going to just talk a little bit about hydrogen to give context. Hydrogen is always being referred to as the fuel of the future, with the rhetorical response was, that's because it always will be in the future and it'll never be realized. But the times have changed. The energy transition is happening at a pace now, and there's a lot of interest in hydrogen and its potential role in the energy transition. In the last 2 years, there's been a surge of investment dollars for hydrogen research and operational projects coming from government and the private sector, not least of which have been the Infrastructure Bill and the Inflation Reduction Act here in the US. So we've got the backdrop of very solid policy commitments and federal government and corporate investment. So in California, we've long had the zero emissions vehicle policy, and we now see hydrogen fuel stations being funded by the state to enable the light-duty vehicle market. And some news from Oxnard last month, the Gold Coast Transit District has been awarded a grant of $11 million for 5 fuel cell hydrogen buses and filling infrastructure. So it's very exciting, and that sort of investment to stimulate this economy is what we're seeing. So essentially hydrogen can be viewed as stored energy. It has a lot of advantages. It can reduce greenhouse gases to zero emissions. It can immediately improve the air quality in industrialized areas with diesel emissions. So health benefits in disadvantaged communities. It can be used in the electric power sector to stabilize the grid when you've got renewable energy coming on at variable times. And it's very, very effective in the hard-to-abate sectors like steel and cement and some others like that. So lots of potential. So to the topic now, we're going to talk about early stage, but these two have so much experience that the conversation will be a well-rounded look at hydrogen, I think. So let's get started. I'm going to turn now to you first, Jack. And you've been at the front end of this 30 years at the APEP at University of California, Irvine. So working every day on the initiatives and ideas to make hydrogen a real viable fuel choice. Perhaps you could share a little on what you're seeing in the hydrogen sector today and how it might be changing, especially how it's changed as well over the last, say, 5 years.
Mm-hmm. Thank you very much. I would suggest that objective analysis of the features that we need to achieve zero emissions in all sectors of the economy that have occurred not only in the United States, but I'd say especially in China, Australia, all of Europe, Korea, all leading the US, by the way, to determine that we need some features that cannot be decarbonized, that cannot be depolluted without the features of hydrogen. And these include things like lightweight, that enables things like aircraft to fly, or ships to sail across the Pacific. Long-haul trucks to carry a large amount of freight a long distance. And then you have rapid fueling that is enabled by fuel instead of electricity for charging batteries. These kinds of things will make a difference, okay? And then we also have very difficult, well, actually impossible to decarbonize sectors like cement and steel. Cement and steel need a reducing gas. Nowadays, we use things like coal or natural gas to do something like that. But why not use a renewable gas like hydrogen, made from either biogenic sources or, most importantly, made from things like sun and wind power through electrolysis, which is going to be the most important way that we make hydrogen. It's going to be the most important way because sun and wind power is available all around the world to greater or lesser extent in various countries, and more equitably than any other primary energy resource. That's where all the hydrogen is going to come from. And it was really the other countries that eventually convinced, I think, us in the United States to, again, objectively look at, hey, how can we really achieve zero emissions in all of our applications? And the only way you can do it is if you add hydrogen to the story that we've already been telling about sun, wind power, batteries, and hydrogen. These features can't be delivered by only those other three things alone. So this is what's happened all around the world. And as a result, we've had a very strong policy statement, again, not just from the United States, which is the most recent one, but from all of these other jurisdictions. Yeah.
So Jack, we'll come back to some of those emerging technologies in a minute, but let's turn to you now, Nita, and now working where the rubber meets the road, or perhaps in your case, it's where your business is literally taking off. So you frequently refer to yourself as a rocket scientist, and legitimately so. So please tell us a little bit about your personal journey, why you left those dizzying days at NASA to come over and start hydroplanes. So up to you.
Sure. So actually my first foray into aerospace engineering was working on the development of launch vehicles at Boeing. And this was the Delta IV program in the late 90s. And the most efficient rocket fuel that you can have is liquid hydrogen, liquid oxygen. So it's a completely ubiquitous thing from an aerospace perspective when you look at it from the space program, and it has to be cryogenically stored, but it's a challenge which was solved for the space program many decades ago. And so that was my first foray into chemical propulsion. But then, of course, I shifted over into electric propulsion for spacecraft applications because that's even more efficient when you can do things electrochemically, which couples nicely to fuel cells. But I think after being in the space program for basically 20 years, I kind of started to think I'd like to do something to help the environment. My primary hobby is actually flying small planes, and so there's a huge number of aviation use cases outside the one that you're used to, which is traveling on transatlantic, trans-Pacific, or Southwest up to San Francisco, that has a tremendous carbon footprint associated with it. And when you look at the regulatory space of aviation, it's actually easier to get something into the commercial sector if it's a smaller platform than if you start with the jumbo jet, right? So from an engineering perspective, it makes sense to start small and work your way up. And then after spending just a few years in the battery-powered transport space, first with the Hyperloop, which in a sense is like an airplane because it has a gross weight takeoff limitation as well as small aircraft. Batteries are just a terrible solution because they're so heavy, the energy density is really bad. So ironically, hydrogen is the perfect solution to decarbonization, aviation, certainly with electrochemical fuel cell for a range of aircraft and maybe combustion for larger jet aircraft, but it was just a natural transition. And so for me, I almost feel like everything in my career finally took me to this point of being able to translate my space program knowledge into a commercial application which would benefit from those unique aspects of the space program which can now be used here on Earth.
So staying with you a moment, Anita, You started hydroplane in 2020, so it's been just 2 short years. What has that journey been like, and what are you have a flight plan, which is your business plan. Where are you at in the journey, and how pleased and satisfied are you with where you're at today?
So COVID actually gave me an opportunity to be grounded here in LA because I was traveling too much internationally, and then COVID put all that to an end, and I was working at a battery-powered company at that time for aircraft, and so then I decided now is the time to do something in the fuel cell space, and so I started the company in 2020 actually utilizing the U.S. Air Force Agility Prime program. So the U.S. Air Force has its own venture arm, which is AFWorks, and you could put in novel technology proposals to that as a small business. So we got the company kickstarted with Agility Prime with a phase 1 contract to develop a custom power plant for actually vertical lift applications, which are really important to the military. And then after we completed that phase 1 effort, we did an angel investment round. We're successful with that, and then we put in our phase 2 proposal and also got that selected by the U.S. Air Force. So now we're working towards our first flight demonstration in first quarter of 2023, and then we can move forward to a phase 3, which is the manufacturing phase, where we would produce a n number of these power plant units for the Air Force application. But one of my personal goals was actually to get the Department of Defense to invest in green technology development for energy decarbonization. And it actually makes a lot of sense because one of the biggest challenges is our reliance on foreign oil. So when you can produce your energy locally, you can produce your jet fuel locally, you all of a sudden remove the dependence on Russia, you remove the dependence on China for lithium. So hydrogen actually has this great geopolitical context where you can actually make a country safer because of it, and obviously the Air Force agreed with that, and that's how we were able to get the program funded. But yeah, we're moving along with our FAT power plant, which is a 200 kilowatt power plant which supports a range of aviation applications and could conceivably also support marine and trucking applications.
So your first flight trials you expect in 2023?
Yep.
So coming up soon. So Jack, back to you. You talked quite a bit in your opening remarks about the production of hydrogen. Maybe you could talk a little bit more about the hydrogen value chain and what basically constitutes the hydrogen economy, because there is compression and distribution and delivery of the hydrogen all the way to the end uses like Anita's. So tell us about a couple more of the alternatives for production, and then some of the challenges in developing the infrastructure to move it around.
Yes, thank you. Let me just say first of all that there are, I think the most important end use for converting the hydrogen back to electricity is associated with diesel and eliminating diesel in our society. Diesel is what's powering our ships. Diesel is what's powering the long-haul trucks. Diesel is what's powering our ports. And what it leads to, in particular, is particulate matter and other pollutants that have a very serious, environmental and health impact, and it's concentrated on certain populations. It's literally killing people right here in LA, right here, wherever we have these freeway corridors. You have enhanced cancer risk, you have asthma attacks, you have all kinds of detrimental health impacts and environmental impacts. And hydrogen's one of the only vectors that can possibly eliminate those diesel applications. But hydrogen isn't as great a fuel as diesel when you consider the thermodynamic characteristics of hydrogen. It's a lot more difficult to actually store hydrogen on board the truck than it is to pump this liquid stuff that we just dug out of the ground. That liquid stuff that we dug up out of the ground has beautiful properties from an engineering and thermodynamic perspective. It's super high energy density, super on both gravimetric and volumetric measures. So in other words, it's super easy to just pump into a little plastic tank and to carry a whole bunch of it along. Hydrogen requires additional investment. It requires investment in things like liquefaction, which again takes some energy, but if we can make that energy from the excess sun and wind power that we already have in our market today, there's not another known alternative that's zero emission.
So a lot of passion there, Zach, about hydrogen's place in the transition that's taking place. You talked about the challenges of cryogenic storage, that's making it into a liquid form. Like hydrogen doesn't liquefy until it gets down to near absolute zero, so you need a lot of energy to do that. Anita, you were planning to use liquid hydrogen in the plane. Are you going to be purchasing that, and then how are you going to get that liquid hydrogen into the plane, and do you have certain challenges with that you're having to solve as well?
Yeah, so it definitely is a requirement to be able to have a efficient useful load on an aircraft platform is to not store it as a high pressure gas as it's done in the automotive applications, but to store it as a liquid. And just for point of reference, if you look at the mass fraction of the 700 bar or 10,000 psi tanks on the cars that you can purchase, about 6 to 9% mass fraction, so that big tank, only 6 to 9% of that is your fuel. But if you shift over to cryogenic storage, it can get closer to 70% mass fraction, so that's obviously a really important technology solution for aviation applications. So one of the hard parts, though, of being a technology company in the end-use transportation space, it's a bit of a chicken and the egg problem, right? We don't control the infrastructure, we don't control access to infrastructure, how are we gonna get hydrogen at the airport? So we are responsible basically for developing these kinds of relationships ourselves. Fortunately, I've been doing a lot of events lately, so I did meet up with Air Liquide, so we probably would get a delivery from Air Liquide into a door, which we would keep at our airport to doing, our initial demonstration flights. But how do you couple that to an operational network is a challenge that we as a small company can't solve, and that's where we require infrastructure, we require local government support to make that happen. But on the technology side, it's a positive thing to store it as a liquid. It's also stored at a much lower pressure, which means that the mass of the tank is a lot less, right? So that's a good thing. But then you also have to have the insulation, you have to have the boil-off rate, so that you don't use too much fuel, but it turns out to be a good solution for aviation. So at the small tanks that you need for the size of aircraft that we're looking at, it isn't too difficult of a solution. Will it be a difficult solution for an A320? Maybe, right? We're not starting at the A320 size, we're starting a lot smaller, but I do think the incremental approach will work out fine. And there's a lot that we can leverage from even pre-existing technologies of storage, vacuum injected tanks, or even insulation, which is being developed for cryogenic storage that we can put onto the aircraft. And we do have a custom tank designed to facilitate that. But our goal as a company was to provide the exact same endurance for a given aircraft platform using our power plant plus liquid hydrogen storage. Therefore, as an aircraft owner-operator, for you don't care. As long as you have access to that hydrogen, that you can still fly that airplane with the amount of payload that you want for the given scenario that you have. And that was kind of like an engineering requirement for us. And the cryogenic storage of hydrogen enables that.
I just wanted to add that all of the modern hydrogen fueling stations that are servicing the light-duty fleets have liquid hydrogen delivered. So this morning, when I was fueling my hydrogen fuel cell vehicle, there was a truck that was there delivering liquid hydrogen. And so it's starting to become more common to have a liquid hydrogen delivery to your site, even if it's in Lancaster. Okay, yeah. So this is starting to become more common to have liquid hydrogen available.
Jack, I want to come back to hydrogen production again in a minute. And an alternative to the renewables is the decarbonization of natural gas. We have an abundance of natural gas, and it's causing a lot of anxiety around the methane emissions and whether we should continue to use gas at all. But here in Santa Barbara, we've got a startup company called C0 who's got a pyrolysis reactor that strips the carbon out of the natural gas and frees the hydrogen to come on into the market, and then the carbon, if it can be commoditized, could be a revenue source as well. Do you think there's a good future for that, or is renewables really the path to go alone?
Well, let me suggest that you may have heard of the colors of hydrogen. How many of you have heard of the colors of hydrogen? Yeah. I mean, I'm a human. So I like colors. I mean, I even like the colors of the rainbow, right? So I think most humans like colors, and this is why the color idea is a good one for relating to humans. But I am against the color spectrum for hydrogen because it's not objective. And it doesn't analyze hydrogen properly for its features. Its features either of low carbon or low pollutants or whatever feature you want to assess. Okay, so I am for green hydrogen. That's a color, and it's a color that everyone I think understands from the very beginning is something that is environmentally sensitive, that is sustainable. Okay, so how long did the Earth take to make the natural gas that we are consuming today?
4.5 million years.
Okay, he says 4.5 million years. That's way too accurate. It's not, I guarantee you it's not that number. Okay. But it's 10 to the 6th, that's only 1 million, to 10 to the 8th years. What? How many years do people think we're going to keep using natural gas? 50, maybe 100, even if it's 500. Is it sustainable? Quite obviously, we're talking about orders of magnitude of years difference between how long the Earth takes to make it and how fast we're using it. Okay, so even if we had no environmental policy whatsoever, it's not sustainable. We can't keep doing it forever. That does not mean that we should not use some of it today. And use some of it today in these very ways that we don't put carbon into the atmosphere, in ways in which we can make a value-added product, don't put carbon in the atmosphere, and we make useful hydrogen that can displace diesel. Okay, all of these things are very, very good from a carbon and a pollutant emissions perspective, but it's definitely not the main way that we're going to do it forever. The main way we're going to do it forever is from sun and wind power. That's what's going to keep coming at us. Every instant we use some of that sunlight up, it's going to keep coming at us. Okay, so these kinds of things I think you have to think about when you're talking about use of natural gas. Use of natural gas also has methane emissions associated, especially with the supply chain. And this, from my perspective, and of course methane, the main constituent of natural gas, has a very high global warming potential. And as a result, we should reduce that as much as possible. That investment is required regardless of whether we use it for making hydrogen or not. Because mainly where that comes from is the long transmission lines that come all the way across from Louisiana to California, and from the source, the underground extraction of those natural gas resources. So we have to invest in reducing that regardless. Let me make one final thing. Investment in carbon capture like this, okay, is very good also for the ultimate future in which we're going to not only use sun and wind power, we're also going to use biogenic sources. Okay, this is super important. Biogenic sources cannot substitute for what we do fossil. There's not enough trees, there's not enough waste streams, there's not enough of that to do everything we need to do. But we still have to manage the waste streams. We still have to manage the biogenic sources. We're still going to have agricultural systems that are going to produce some wood waste. And okay, so one of the main ways that we should do that is also to do carbon capture, hydrogen production, and have negative emissions associated with these biogenic sources going through the same sorts of routes that you're talking about here with C0. Is that the name of the company?
C0.
C0. So these are super important. They are not the main way we're going to make hydrogen, but they're important ways of making hydrogen into the future.
So one more for you, Jack, before we come back to Anita, and that is electrolyzers are a promising pathway for hydrogen, renewable energy conversion. So we hear about the use of platinum group metals and a very expensive, limited resource that they are. Are they going to become, you know, a bottleneck and a restriction for the electrolyzer pathway? And what research is needed there? And do you see any breakthroughs where we can solve that to really get this thing going? And by the way, platinum is used in the electrolyzer to make the hydrogen, and often in the fuel cell at the end point where you bring it back. So it is an issue.
Well, first of all, I agree that platinum group metals, we use both platinum and iridium in electrolyzers and fuel cells at low temperatures. And those low temperature fuel cells and electrolyzers are super important for our conversion. They are the highest power density, lightest weight, so we got to use those in aircraft and things like that. And they could, and actually will, I think, constrain the number of applications that we can sustainably power or fuel, okay, with hydrogen and fuel cells using proton exchange membrane technology. We can't do all that we need to do with hydrogen with only that technology. I think because of this platinum group metal constraint, okay, platinum and iridium especially. I want to say, on the other hand, that platinum and iridium in these applications is highly recyclable. As a matter of fact, you may know also that platinum, which is also in your catalytic converters, this is why people are stealing them, right? Okay, platinum is highly recyclable in those applications as well. So we can recycle a whole bunch of it, but still, these are very precious and very expensive resources. So we can't do everything with PGM, platinum group metals. But we have alternatives to that. We have alternatives that are associated with alkaline electrolysis and alkaline fuel cells. We have alternatives associated with solid oxide electrolysis, solid oxide fuel cells, which are very low TRL technologies still today. And so I think that there's going to be innovations both in the low temperature and in the high temperature electrolysis and fuel cell space that will enable us to actually do the rest of what we need to do. We're going to still use some of the PEM cells, definitely. Especially, again, if you're flying an aircraft, you want something lightweight, it's the lightest weight one we know right now. So we got to use it in some applications. And it will constrain it, but it's not the end of the story. The end of the story is invest in some of these other ones too. Yeah.
So this conversation itself could go on for an hour or two.
Yeah.
But I want to change now to the topic of investment, and how important is investment to bring these technologies out of the labs that you associate with, Jack and Ren, and then to you, Anita, with a startup. It's a challenge, but let's ask you, who were your initial investors? Angels, family, friends, VC firms. Anita, how did you get the capital? You mentioned the ARPA grant, I think, the federal grant you've got, but you needed more money. So how did you approach that, and how hard was that for you to get the funds you need? You've got a very impressive team. They all need to be compensated, so you have to have enough money always to be able to bring it forward.
Yeah, so obviously I'm an engineer. I'm not a business person. I am not a finance person, so my experience isn't with the capital markets and venture capitalists. And as an engineer, sometimes we find venture capitalists to be disturbing because we can't figure out what they're motivated by. Which is money, by the way. Yeah, exactly. and so that of course is learning experience for anybody who's transitioning from engineering, to the VC world. And so our first round actually was an angel investment round, and we did talk to some VCs, but the VCs were definitely more focused on well, are you going to give me a good ROI in the next 2 years? And of course not. In the aviation space, the regulatory environment is such that you couldn't get a product to market in such a short period of time. But one of the reasons why we went the government route is I saw another company who did the same thing, which was Joby Aviation. They also went through the Agility Prime program. They went through the phase 1, the phase 2, the phase 3. I think they're still in their phase 3 now, but they were able to use that to get government investment, to be able to create a governmental use case where you get around airworthiness certification that the FAA would put in. You can fly it directly for an Air Force use case, because we're all part of the Air Force in terms of the program that we're in. So that's one way that you can take something which is highly regulated and actually start making it generate revenues off of it by manufacturing it for the government customer. But I think the angel investment community is better because they're more mission focused. They're more focused on how can I take my personal wealth and advance goals of society. So that's where we went, was the angel investment route. That being said, there are energy funds, but I think there's probably not enough of them, and I think they're still a little bit too coupled with the VC space. And when you look at the VC space, and this is a fact, 2% of venture capital goes to women-funded ventures. Even less than 2% goes to minority-funded ventures. So unfortunately, because of that, when you are a woman, when you're a minority, you're already at a disadvantage to be able to tap into that space. But I think on the angel round, if you're mission-focused, that doesn't count. I think angels invest in everybody if they believe in your mission. And if you go through a meritocracy process, which is, with competitive proposals, technical proposals, which is what we did, and we submitted one to NASA recently. I think that's another way to do it. But I do think that angel community is better for these climate-focused developments for the seed round, because you want your investors to believe in your mission and to support you in your mission, not try and cash out quickly, right? It's like, we're trying to help the planet, not our pocketbooks.
So you're 2 years in, Anita, but do you see now the need to go for a next round of funding to keep this going, and what does that look like for you?
Yeah, so we're going to do our next round, coupled to our next milestone demonstration, which is our stack testing on the ground, as well as our flight demonstration. And also part of one of the strategies that you can have as a small company is you can dilute yourself really quickly and raise a lot of money early on, or you can take this incremental approach, make progress, build value to the company, and raise more money. So for our next round, would allow us to scale up to manufacture the units for a variety of customers, whether that's the experimental aircraft community, the government aircraft community, or eventually the small aircraft market, including helicopters. But so we're going to open up another round in the next 6 to 12 months. And we're still not raising that much money. So I think we're looking at like a $5 to $10 million round. So, we did a $2 million round, so the next one will be a $5 to $10 million round, which we would then couple to our next phase of our Air Force contract. So the good news is that when you don't try and bite too big of a piece of the apple, which is like building an entirely new aircraft, and you just focus on the key technologies to develop, you can actually do that more cost effectively, requiring less capital. It's actually easier to integrate it into existing platforms as opposed to, I'm going to go off and build an entirely new aircraft, right? That's what the Boeings and the Airbuses of the world should be doing, because that's their business, right? But for other companies where you're in the technology space, so what we focused on instead was coming up with a more efficient membrane, right? So we can operate it at higher current densities, that we can make it more durable for the aviation application, and also focusing on a new catalyst technology, which would allow us to basically, get more performance out of the fuel cell, which would then end up increasing our specific power, which reduces weight. And so that is integral to being able to fly a fuel cell for an aircraft to give you the same useful load, but it also naturally couples perfectly to the marine sector as well as to the trucking sector. But aviation is the forcing function. Aviation is the hardest thing to decarbonize because of the regulatory space, but it kind of helps everybody along the way.
So I'm going to switch to you, Jack, on this same topic. I think I once heard you say that you see all these technologies in the lab, and one of the things that you really wanted to see happen was to have investment to take them out of the lab and move them into commercial reality. So how many of the technology types that you get involved with actually lead to spin-offs? And if you can think about that over 30 years, how many of them are actually really successful, and what does success look like?
That's an interesting question. Interesting aspect of that question, because I was thinking the whole other time about a few other things. But let me first answer that, because I'm very, very proud that some of the students that have been mentored by me and my colleagues in our labs have been very, very successful in their entrepreneurial spirit in developing companies that directly resulted from things that we had been studying in the lab. So for example, I have a student who has developed a solar company, okay? A student, and it's mostly successful in China. And it's mainly for optimally designing solar systems, no matter what the architecture of a building is. Okay, so this is one of the companies. Another company is associated with two students that graduated from our program that started First Element Fuel, okay? A hydrogen fueling station company. They've built more hydrogen fueling stations than any other company in the world. Whoa, that's pretty dang cool. Okay, another company is Altura Associates, a green building company, where they try to basically do things like LEED certification of buildings and try to make buildings as low consuming as possible, but also integrating solar and all kinds of things into the building, integrating battery energy storage and zero emission vehicle charging into their buildings. They're famous for doing this. So one of the things that I'm most proud of and excited about as a professor is the fact that I get to interact with so many super smart, talented, and ambitious people year in and year out, always new thinking, always new ideas and everything. I mean, I'm so fortunate to have this job where I get to do things like that. I have companies that emerge from graduates, okay? Super cool. But the other thing that I do intentionally, and maybe it's because I grew up on a farm, and I like to see how things really work, is I do a lot of very applied research, things that actually involve a company that is interested enough that they want to support it financially, but then of course to take the learnings from that research and to actually use it in their industry. And this again, I'm not that interested in discoveries that don't go anywhere. I want discoveries that are going to actually make a difference. I want discoveries that are actually going to have an impact on people's health, on the environmental health, that are going to change the world by introducing zero emissions into all these sorts of applications. So, but I wanted to say that our very best product at UCI is our students, our graduates. They're the ones that are really changing the world.
So those students, those graduates, Jack, they're the ones that take these ideas forward, and if they're successful, they will find investors to come with them in these exciting things that they're bringing out. So I got one last question, we'll open it up then, but this one is to the topic, the importance of early stage investment to leverage this massive economy that we're seeing coming. I mean, the projections are California is saying 4 times as much hydrogen in the next 10 years. The Hydrogen Council says 6 times as much hydrogen globally by 2050, and the banks are saying, we've got a $3 trillion market by 2050. That's huge. But what's the role, or how does innovation and early stage technology advancements like yours, and how does that stimulate, and why is it necessary to accomplish that very laudable goal that we have? So maybe I could start with you, Anita.
So I actually think that everybody's heard the term disruptive technologies, and I think early stage investments, which by definition are being done by either funds or private individuals, they're able to tap into startups that are creating brand new high-risk technologies which would never be developed, in the Airbuses and the Boeings of the world, the Pratt & Whitneys, the Rolls-Royces of the world. So you have to put the money into these much smaller entities that are coming out of universities, that are coming out of people who are entrepreneurs who have expertise in the space, to be able to completely disrupt the way things are done, right? And you take a look and I hate to use this as an example, because I don't think Elon Musk is a good example of like a small founder, right? Because he was a wealthy person, right? But he was able to disrupt the car industry because, the traditional automotive sector did not want to, invest in batteries. And the same thing in the aviation space. The Boeings and the Airbuses of the world have had decades and decades to do something to decarbonize, and they've done nothing because they don't have to. It's business as usual. So early stage investment can create these new high risk, huge return on investment technologies to completely disrupt the way things are done. And without those dollars, it won't be done, or it'll only be done with people who can self-fund themselves, like the Elon Musk of the world, right? So by early stage investment, you can help smaller entrepreneurs be successful, not just limit it to the Jeff Bezoses and the Elon Musk of the world. And I think that's what I personally feel this every day, right? Where I have to get investment from, the angel community, from the VC community, otherwise I would never be able to make my thing become a commercial reality.
Yeah, well, let me add to that we already know how we build these electrolyzers and fuel cells today. And we know that if we just got a very large order, we could make them cheaper. Okay, so we know that scale is going to make a difference. It's going to bring them down in cost. And as a matter of fact, there's science behind these learning rates and types of things that show it's going to come down in cost. But if you only did that, we would never be able to achieve the goals that US DOE has or that others have for displacing fossil fuel. We cannot, by scale alone, get to the numbers we need. It needs to have both scale and innovation. We already know that we have to reduce the amount of platinum that we use in these electrolyzers and fuel cells, and we got to make them last longer. And there's innovations associated with doing that. We already know we got to make pipelines that can actually transport this stuff over long distances, and they can't transport it yet. So we have to invest in the infrastructure that can move things more cheaply and at lower cost than we are today. This liquefaction idea, or that Washington State University has, could help. Right? All these innovations will matter in the end to eventually deliver hydrogen that is lower cost than the current fossil resources we use today. And when that happens, then it will be desired by all peoples of all nations all around the world in a way that can effectively displace what we're doing today with fossil. Okay, but you need the innovation to get to the number.
And the innovation needs the investment, and
Okay,
this
yes,
innovation
exactly.
investment
Yes,
begins
exactly.
right now.
Yeah.
And the earlier we can get these breakthroughs into the scale-up and commercialization, obviously the better place we are.
Yeah.
But the innovation is going to continue
Yeah.
all the way to 2050 and beyond to make the hydrogen the very best fuel alternative it can be. So I've really enjoyed this Q&A for the last 50 minutes, but I'm going to open it up now to the audience and take a few questions before we round it out. So Craig, you were up really quick here, so over to you.
So there's a company being incubated out of UCSB that is doing a solid hydrogen oxide and has a stable, has an innovation to get a stable stream of hydrogen out of that, and arguably it's mostly for flight applications, because you get that mass index to pretty much 100% instead of 70 with the liquid. It's called, the name of the company is Tesserol, so y'all probably haven't heard of it yet. But how important is it to, your views of the world, this question is all three of you, a solid hydrogen oxide that can get a stable stream of hydrogen out of it? How important is that to your perspectives?
So Jack, do you...
No, let me ask it.
Let me ask a couple of questions. If you say hydrogen oxide, that means it has some oxygen in it. Every oxygen weighs 16 times as much as every hydrogen. I'm trying to figure out how you're getting to this 100% number when she's at 70 already. Okay, sorry.
I knew I was on tenuous
Okay.
asking this question, but it's basically they have a solid state hydrogen and they get
Solid state
Yeah.
hydrogen storage technology.
Yes.
Okay, but what is the material that is used to store the hydrogen? Is it like a metal oxide or something like that? So is it like...
I believe it is.
Yeah, so this could be like a metal hydride type of storage, which is actually very, very heavy because of the metals that are used in it. It wouldn't be necessarily applicable to aviation applications.
Well,
It could be...
It's being targeted to aviation, so I know it's.
So I'm trying to figure out what it is then.
It's
Do you happen to know what it is?
I don't. I mean, I would certainly, to answer more generally your question, if it ends up being lighter weight, then that's obviously a positive thing. But ultimately, it still has to be converted into the hydrogen to run it through the fuel cell. But anything which would reduce, the mass fraction in terms of how it's stored is going to be positive for aviation. That being said, nobody's yet storing it as a liquid, so there's still a lot of gains to be made by that. And I think the one issue I have with any business model which restricts the fuel supply to a single company, it's almost anti-competitive, right? It's sort of like how, Apple only has these interfaces, you have to buy all the Apple hardware. So when you think about it, more about like how are we trying to decarbonize the industry, if it becomes you have to go through this funnel to be able to get access to your hydrogen, that may not be the best solution, right? So that's the only thing I worry about is that type of model where it becomes not anti-competitive, but anything which would reduce the weight obviously would be a good thing. But I'm just not familiar with their technology, I suppose.
Yeah, Craig, we'll follow up later. I'd like to get more details and
Yeah, I
talk
would
further
too.
about that.
I'm interested in what that is.
Right. So a couple of hands in the back. Cheryl, you want? No, come to you.
Yeah, no, I'll just stand over here. We have heard that the production of hydrogen is fairly water intensive, and in California, that's of course a major issue. So I wanted to get your thoughts on, how water intensive is the production of hydrogen, and are there innovations happening right now to try to be more efficient in using the water to produce hydrogen?
Jack, and start with
Yeah.
you.
That's a very good question, and it's something that in California, but in many, many places all around the world, we should be careful and concerned with. Making hydrogen from electricity through electrolysis of water is very water intensive. It's very water intensive. On the other hand, if you compare it in the power sector alone, I'm just going to use a couple of anecdotes, okay? In the power sector alone, if we made all the power that we currently make from natural gas via electrolysis of water and hydrogen consumption, we would use less water than we currently do for making power. Okay, and this is kind of a remarkable statement, right? So if I use water directly to make the fuel, you mean I use less than I do if I just dig up natural gas? Yeah, you do. And that's mainly because we do use a lot of water in the power sector. In addition, if you compare the water demand that would be required for a very robust hydrogen economy, let's say hydrogen that serves 20% of all energy demand in society, okay, this would be very big market. This is the 3 trillion thing that you're talking about. That would use 1/10 of the water that we use in agriculture. Okay, so you start to say, okay, yeah, when it comes to like the amount of water, it actually could be less. And secondly, the water is naturally returned when you convert it through a fuel cell to actually make the electricity again. So there is some virtuous cycle that the Earth can manage over time. Okay, so the amount of water could be way less than we currently use for energy. Okay, all the analyses I've seen that objectively look at it say we use less total water.
And Jack, I think
This-
that's true for refineries as well.
Okay, refineries is another place they use a lot of water. If we actually put the made hydrogen out of it, it would be better. Okay, but let me just say that that doesn't mean that we don't have actually a very big water challenge. Why is that? We are not only going to make hydrogen where we currently have power plants. As a matter of fact, where we're most likely to make it is where we're going to put new sun and wind power. And where is that? Well, that's mostly in the desert regions here in Southern California, and we don't have a lot of water there. This is a very big concern for the community, okay? And so this is why it's a very good question. It's not that the Earth doesn't have enough water, or that the Earth couldn't manage the cycle forever, okay, of using water for making hydrogen. It's mainly that we don't have it in the places that we think we're gonna need it into the future. So, how that's going, that could be also involve a lot of innovation. And one of the things that we're studying at UCI right now, I'm sorry, I'm going to get into this, is can we harvest water from the sky in the desert? And there are really interesting ways in which you could put coatings onto photovoltaic panels, in which at night they would radiate out into space very effectively, so that those surfaces became very cold, and we would actually take water out of 2% humidity air. We can do it. Okay, so I don't know if this is going to be the technology that's going to work or something like that, but okay, these kinds of things I think might make a difference, because the water isn't necessarily where we want it for this zero emissions future.
Thank you.
Yeah, thank you.
I think the only thing I'd add to that is that, you know, it's a systems engineering problem, right? So where you can't just focus on one element and just try and optimize that element. So you have to think about everything. And in terms of like wasteful water usages, I went to a presentation, I think it was by Unilever, and I think they must make some type of beer, and there's something like 10-to-1 the amount of water that they use versus the amount of beer that it's made. And the fashion industry, also another incredibly, you know, wasteful source of water. So having conservation methods for everything to conserve water is more important. And if we're trying to combat climate change and the temperature's increasing, then obviously you're also running into other issues there, which is consume more water. So we have to think about the most efficient way to decarbonize, to reduce our CO2 output, which then prevents a lot of other challenges which are going to happen downstream, which would result in more water, and come up with ways for all industries to be more conservation minded in terms of how they use water, so then we can put water into the energy production. So it's very much we are a system. We have to think about all the different aspects of the system and the best way to optimize it. But to not do it, right, because of the water consumption and then stick to the CO2 output is worse.
Yeah. Next one, see.
As an investor, we'll talk to people who've worked on hydrogen fuel cells before, but maybe they missed the boat, or for some reason they moved on from that to ammonia or methanol, and now they're singing the praises of ammonia or methanol. It's easier to store, or it's less hazardous. I'm curious, how is there a scenario where ammonia or methanol would be more appropriate, or is it all just different flavors of hydrogen?
Right. So, for those of you in the back who may not have heard the question, what about methanol and ammonia as alternatives to hydrogen being easier to store, as a fuel? So, Jack, again, come to you first.
So you're correct that Ammonia at very low pressures is a liquid, and as a result, pretty cheap tanks can store a lot of energy in the form of ammonia. And similarly, methanol at room temperature and pressure is a liquid. So these types of alternatives could be energy carriers that we use into the future that are more like the fossil derivative fuels that we use today, right? Like gasoline or diesel, where you can pump it into a cheap tank and carry a lot of energy around. It is easier than hydrogen. I want to make a couple of points. The first is, how do we make that ammonia? We make it today from converting natural gas and producing hydrogen from natural gas, and then reacting that hydrogen with nitrogen to make ammonia. So ammonia could be a renewable hydrogen derivative fuel. And certainly we could make green ammonia, as it's often called, okay, from green hydrogen plus nitrogen for the fertilizer applications that it's used. It's sold as a commodity, as a fertilizer all around the world and shipped all around the world. Okay, so and then the same goes with methanol. How do we make methanol? We make it from natural gas today. We could make it from sun and wind power, okay? And react carbon, or carbon dioxide, with the hydrogen that we make from sun and wind power to make the methanol. So, methanol and ammonia are viable energy carriers, but they're renewable hydrogen derivatives. So we still need the renewable hydrogen, even if you're going ammonia or methanol route, okay? That's the first contention. Second contention is that there are some reasons to select ammonia or methanol, most of which are associated with the ease of storing, but both have toxicity concerns. Okay, ammonia is very toxic. Methanol is toxic. It's totally odorless. It looks just like water. You could drink a glass of it and not know that you drank methanol, and you're blind. Okay, or you die. Okay, so these kinds of things people are concerned with. And ammonia, if you breathe some of it in, I mean, you could die from breathing it in. And ammonia accidents are some of the worst accidents in industry today. Okay. So there's not anything perfect about those solutions either. We put a little more energy in to carry hydrogen around. And from my perspective, in most end-use applications, maybe not all, maybe ships are going to be fine, okay, with ammonia and methanol. But I'm going to guess on an aircraft, I'd rather have liquid hydrogen on board. Okay, it's going to be lighter weight. Okay, we're going to have an ability to carry a lot more energy around. I think it's going to be safer. Okay, on cars, I don't think we're going to use ammonia or methanol. Okay, on long-haul trucks, no. Okay, we're going to still need it for ag. Okay, so I don't know. So these are my contentions. So you still need the renewable hydrogen to make the stuff, and then only in limited applications do I think it's going to apply. And maybe ships.
The only thing I would add is I agree with everything you said, and I also feel like it's a bit of a distraction to focus on technologies like that instead of, I think, the better solution, at least for the aviation use case, which is just go directly to the cryogenic storage. Because at the end of the day, there is a limited amount of money, right? And so if it's allocated to something else that still keeps you from getting to where you really want to be, then you just don't get there. And so that to me is a bigger issue. That being said, I believe NASA did actually fund a ULI recently, which was based off of ammonia storage, which was a little bit, I thought, unfortunate. Because, but I will say this because I'm always checking out the NASA calls. They are also focusing on hybrid electric, right? Still burning hydrocarbons. So it doesn't mean that they're actually making a good decision, by the way, in selecting these technologies. And there's a whole, you can ask me that on the non-recorded Q&A section. But I actually think that the better solution for the aviation one, for the highest specific power application, is as it's done in launch vehicles, should be done also for aviation. And all those technologies can be leveraged in these other sectors to make them more efficient. So I would just rather a smarter way to get to where we really want to go.
So time is moving on. One more question, if there's one out there. Not seen any hands, so obviously it's, okay, Dennis.
I'll throw one out because I have the pleasure of serving on the airport commissioner in Santa Barbara. And when my regulator puts out a bulletin on design for future eVTOL ports, got my attention. We're in the process of building and designing a new parking structure, which is somewhere between 3 and 6 stories. And we're going to push out our terminal 100 yards, 50 yards maybe. seems to me that we should be incorporating the design of the eVTOL port into the top of that parking structure. But maybe we should be accommodating future hydrogen fuels for that. How can we bring this into the planning process now instead of 5 years from now when the project's complete?
Anita, this one's got
Yeah,
your
okay.
name on
It's not
it.
your name on it, that's for sure.
So this actually couples to the earlier question about like how capital is spent and how venture capital is spent. And over the past, I would say, almost 10 years, so much VC money was spent on flying cars. I know because I worked in the space. And in my personal opinion is when you have a technology, you should be solving a problem, not just creating a new solution to something that maybe didn't need a problem. And so I personally think that a battery-powered aircraft isn't solving a problem that needs to be solved. Like you could, ride your bicycle, you could take a scooter, you could, take a bus. Do you really need to fly, 20 miles in an eVTOL? So there's a part of that, which is the reason why there was a decade that was spent in developing these new technologies, and therefore that's the first to get to market, but will it ever get to market? I don't know. But I agree with you. I think this is an opportunity to think about what kind of new renewable energy infrastructure can we have at the airport, and I would argue hydrogen and maybe also charging stations to charge cars as well as your FEV and your BEV. But I think this is simply an example of billions of dollars that were spent in this eVTOL space because the hope was that batteries could help to decarbonize aviation. It doesn't work because the aircraft can only fly really short range distances, and that's the only use case then becomes vertical lift in urban environments where you want to go from this point to this point. So I think that's part of the problem why that's the case. But this is what irritates me though, because if those hundreds of millions of billions of dollars were spent on developing better decarbonization technology instead of the sideways path, we would already be there. And that really kind of upsets me because it's sort of like, oh, it's a wasted opportunity. But I do think if you are part of the planning, actually do talk about that. Well, how could we bring hydrogen to the airport? Because the way that we can make our regional travel carbon emission free is by having hydrogen storage in liquid form at the airport, which can also help cars who want to refuel as well. So this is an opportunity, I guess, for you to kind of bring that up.
We'll mention it at tomorrow evening's commission meeting.
All right.
Okay, so we got one more hand, and then this is the last question.
All right,
Okay? Yeah.
So why do you think fuel cells vehicles were not the next big thing instead of electric vehicles? Because I know the technology seemed to be there, Honda's making them, and it just seemed to be much more feasible.
So I own a Tesla, and I own a Mirai. And I drove the Mirai up here today because I live in Irvine, which is 127 miles away or something like that. And both of these technologies are required for our zero-emission future. And as a matter of fact, if you have a short distance and you don't have to carry a big payload and you don't mind waiting a while for the car to refuel, battery electric is preferred. It's preferred because it is more efficient than the hydrogen route. But these are the only two zero-emission technologies we know. And from my perspective, as a result, both will be used in all sectors of transportation. And again, it's because you have different requirements for different technologies. And let me suggest that the reason that we have more battery electric cars on the road today than we have fuel cell electric vehicles on the road today is primarily twofold. The first and most important reason is infrastructure. Most electric vehicles are charged at home. There's the infrastructure that goes to your house that can fuel your vehicle. Okay, so that would make it a lot easier to adopt. Then the fact that we have to build hydrogen fueling stations for anyone to drive any single, even just one hydrogen car requires an investment in brand new stuff that's not out there in society. The second reason is that we've invested way more in batteries up to this point. It's at least 10 times, I think it's more like 50 times the amount of money that we've invested in battery energy technologies than we have in hydrogen and fuel cell technologies. And as a result, I think we see a much greater adoption. In the end, I think that for light-duty applications that are mostly like commuting and things like this, we should use batteries. It's going to be the preferred technology. But then there's going to be a spectrum. There's also going to be a spectrum in heavy-duty. Some heavy-duty applications can use batteries. Okay, but other applications are going to prefer fuel cells because of its lightweight, enabling a heavier payload and a longer range. Okay, so don't pit these technologies against each other. Both of them are needed for us to get to zero emissions, right?
So they're complementary.
Both are needed. Yeah. What'd you say?
So they're complementary.
Yes, they're complementary. Absolutely. Yeah, thank you.
The only thing I'll add to this, which has got a bit of an investment flavor, is that when you're a startup, like your job is to do a prototype, do a demonstration as quickly as possible, it is a lot easier to do a demonstration with batteries, like orders of magnitude easier than with fuel cells. It's also easier to do something with off-the-shelf technology, right? So, but if you really want to be innovative, you've got to do the more difficult thing. You've got to take on the challenge, and so that's where it's really important to invest in those like key technologies. And so there's just a longer time constant in getting the more complex system to market, but the payoff is way better in terms of the efficiency, in terms of the carbon footprint, and in terms of the total energy storage capacity. And so aviation is a great example, because if you look at the endurance requirement for an aircraft, if you're only flying an hour, the specific energy for the fuel cell system is maybe like a factor of 2. If you're flying for 3 hours, it's a factor of 5. You're flying for 5 hours, it's a factor of 10, right? So for the total stored energy is where you get the benefit to shift into the fuel cell technology, because you're not carrying additional fuel cells, right? You're just carrying additional fuel. But I think it was just the low-hanging fruit solution that led people to looking at the short, simple, quick-to-market use case, but it really wasn't the forward-thinking solution of what is the evolutionary technology to get us to where we really need to go. And that, I think, is important when you make investment decisions, is invest in the evolutionary technology, not just the quick fix.
I think that's a great place to wrap up, and I think for me, the single thing that is most significant coming away from this is how Jack says, you know, hydrogen is absolutely essential to get to zero carbon emissions. We cannot do it alone with batteries or other technologies, so one way or another, hydrogen will play a big role in the energy transition, which is where we're going now. This was a fabulous experience for me to interview these guys, and I think we have really enjoyed a very rich discussion on hydrogen, and maybe give a round of applause to thank you both. So Cheryl, I think we are done, right? So over to you.
Oh no, I have no remarks. I'm panicking.
No, just say, go.
No, I just want to thank everybody for coming. We are technically here till 6:30. If there's any networking you haven't done, please feel free to do so. And if not, enjoy the rest of your evening. And thank you very much to our panelists. One last round of applause.